Hello and welcome back. In this lesson, we will be looking at what we mean by explicit function versus implicit function. Okay? So what does it mean when we say an expression or an equation or a function or just a relation is explicit? Okay? So defining y as a function of x. So when we define y as a function, when we express an equation or a function, it's usually some value of y expressed in terms of x, or x expressed in terms of t, and so on, right? So here are some 5 functions, or what you might refer to as equations, if you like. So 5 functions here are given, all right? In these 5 functions, if y is the subject of a function or the subject of an equation, we say that y has been defined explicitly as a function of x. So if y is the subject of the equation or subject of the formula, then we can say that y has been defined explicitly in terms of x. So equation, the first equation there and the third equation there, we can say that those are explicit functions. They are functions in which the value of y has been defined explicitly in terms of x. So y is on one side and x is on the other side. All right, so y is defined explicitly. If that is not the case, that is, y appears with x on one side or on both sides, so y is on the left and is also on the right and so on, then in that case y has not been explicitly expressed. We say that it has been expressed implicitly. So we still have y being expressed in terms of x. In this case, y has still been expressed in terms of x, but because y is not the subject of the formula, we say that the value of y has been expressed implicitly. Okay, so in the second equation there, the fourth equation and the fifth equation, we say that the value of y has been defined implicitly as a function of x. Why do we need to talk about this? Right, here is a question in which y has been expressed implicitly. In other words, y is not the subject of the formula. Can we differentiate this function? And the answer is yes. And what we are used to doing to differentiate this has been to make y the subject of the formula. So we say y is 3 minus 2x there, like that, and then we will say, I can write this in one step, but I want to write it so in a manner that you will understand the subsequent problems we will be solving. So I'll say, therefore, d by dx of y must be equal to d by dx of 3 minus 2. 2 does not take part in differentiation, or maybe let me just write this together for the initially, and I'll say d by dx of 2x, like that. Of course, we don't normally do this. We can write this in one step, but I want you to understand something here. And so this is my dy by dx, all right? And the derivative of a constant is 0, so this is 0, minus 2 does not take part in differentiation, and then we are left with dx. We have dx by dx, which cancels, it becomes 1, and so we can say that dy by dx in this case is just -2, and that's how we would differentiate this. This is the method we have been using so far, that is, making y the subject of the formula and then saying dy by dx is whatever we'll get on the right hand side. This is what we've been doing so far. But the reality is that we don't always have to make y the subject of the formula. In fact, there will be times when it is completely impossible to make y the subject of the formula. Let us look at such examples where we cannot explicitly express y as a function of x. And so, as I've said, we don't always have to first define y explicitly as a function of x in order to be able to differentiate it. In fact, there are cases where we have relations. Relations are not functions. Relations where the value of y cannot be separated explicitly. Look at the following relations and try to make y the subject of the formula. All right, here is one case. You can see this is y cubed and there is a y here. Trying to make y the subject of the formula sometimes is possible, but sometimes is not. So this is like solving for y. All right. What about that one? In this case, it's almost impossible. It is, in fact, not possible to make y the subject of the formula. Y is appearing in there as an argument of sine function, and it's also appearing as an argument of the exponent there, e power y. Okay? So in such cases, it is impossible to make y the subject of the formula so as to differentiate the way we did. The method of implicit differentiation involves differentiating these functions without having to first make y the subject of the formula. Okay? What I've done is I've tried to draw these graphs to show you that they are not functions. They are relations between x and y, but they are not functions. That is, we do not have a one-to-one mapping or a many-to-one mapping. In these cases, we'll have instances where x has got two or three values of y, or even more values of y. I've drawn some of these functions, so let's take a look, and then we'll proceed. So here is the function x power 3 plus 2y cubed minus 3xy equals 0. If you sketch this on your calculator, this is what you get. And you can see that this expression or this relation fails the vertical line test for function. So this is clearly not a function. We can still differentiate and find the gradient at any point along this relation. Okay? Here is another one that I found out. So this one here, when you differentiate this also, you can see again that this is not a function because it fails the vertical line test. Okay, another one which I made for myself and I would refer to as the tree function. Looks like stems of a tree and branches falling off, or coming off the stem. This is this function here. All right, and you can see that this definitely fails the vertical line test. If I draw a vertical line through this end, for example, I will find many values of y with the same value of x, and therefore this is not a function. It's still a relation, but we can differentiate it. Okay, so how do we differentiate such functions? We will start easy and differentiate one of these functions implicitly. In other words, leaving it in such a manner that we do not make y the subject of the formula. So to differentiate this, we must use the residue idea that we discussed earlier. So in lesson 3.1, 3.1, we showed the idea of a residue that remains when we differentiate some functions with respect to a different variable. All right. Here is an example number 1. Given that x cubed plus 2y cubed equals 1, right, find dy by dx. So basically differentiate this function. So to do that, we're going to differentiate them separately. Okay, this means that we need to differentiate with respect, if we are looking for dy by dx, meaning we have to differentiate with respect to x. So this is important, right? We are differentiating with respect to x. So what do? We start by differentiating each term by itself. So we will write d by dx of x cubed plus d by dx of 2y cubed must be equal to d by dx of 1. Now the derivative with respect to x, so this is x and x, so the derivative will not have a residue. So we're going to have a value of 3x squared there, all right, plus the derivative of this function. The 2 does not take part in differentiation, so we'll take it out, and then we have d by dx of y cubed, all right. In this case, we are differentiating y with respect to x, and so we expect a residue to result, right? So we have our 2, then we get our 3y squared, but now we have to add the residue dy by dx. The derivative of a constant is 0, and therefore this has to be equal to 0. And if we rearrange that formula, if we rearrange that expression there, we get dy by dx is minus x squared over 2y squared. And so we have differentiated this. We found dy by dx without having to make y the subject of the formula first, without having to express y explicitly. All right? So we say we have differentiated implicitly. Right? If you have any question regarding this, let me know and I will come back to you. Otherwise, in the next lesson, we will be looking at the derivative of certain implicit functions and equations. Okay? Thank you very much. See you in the next lesson.